Good afternoon. Yes, today we'll take off this operation planning and control of the semester 2. Now to start with, we'll, I've already discussed previously. What do you mean by operations? Operations is nothing but the transformation of inputs such as men, machines, material, money, information and energy to desirable outputs in the form of goods and services. So, when you talk about productions or operations, which nothing but is a transformation of inputs into output, and the outputs are generally maybe goods or services which comes to the use of the consumers. So, when you talk about productions, we generally divide this production into three categories. That is flows of, jobs of, and the project. Yes. The flows of exist when the same set of operation is performed in sequence repeatedly. When a task is repeated frequently in sequence in a particular order, we call it a flows of. And the jobs of exist when facilities are capable of producing many different products in small batches. And the project is a major undertaking that is usually done by only once. It consists of many steps that must be sequenced and coordinated. So to start with our discussion, I may just say that a productions which is a transformation process may take different categories. It may be a flows of, or sometimes it is called mass production system, where standardized products are produced in a particular sequence and it is repetitive operations. When you produce different products in small batches, it is called jobs of, and project is a major undertaking which is generally taken once in our lifetime. Now, what is the nature of mass production? We'll today take off the topic mass production. Now, if you go through the nature of mass production, it was Henry Ford who in 1913 introduced the assembly line and notion of mass production. So, when you talk about mass production, we generally think that the product are for masses or it produce production in million or for the masses, though it may be an outcome, but it is not exactly the same in meaning. Mass production refers to the manner in which a product is produced. When you talk about manner, this involves the decomposition of total task into the minutest elements, in the smallest elements, shown usually on a precedence diagram, and subsequent regrouping of these elements according to the norms of production. So, an assembly line consists of workstation in sequence where at each workstation the above carefully designed portion of work is done. Mass production requires that all parts of an assembly line be interchangeable and that all parts be replaceable and characteristics which permit production and maintenance of large quantity. So, coming to my first slides, I may say that mass production does not refer to production in millions or production to the mass. But in other hand, mass production refers to a system, production system, to a production process where the total task is divided into smallest elements, which is shown in a precedence diagram. That means it is divided in such a way that a particular sequence is to be maintained. Then after the task is over and they're regrouped again. In a mass production and assembly line, they go together. So assembly line consists of various workstations. And how the workstations are positioned? They are positioned in a sequential order. And in each workstation, above carefully whatever work we have divided, that is to be done. And mass production requires that all parts assembly line. So if I say that mass production is the manufacturing of large quantity of standardized products after using assembly line or automated technology. Mass production facilitates mass production facilitates the efficient say production facilitate the efficient production of large number of similar products. For example, mass production manufactures many identical goods at once was a product of the Industrial Revolution, and Henry Ford's Model T automobile is a good example of early mass production. So, when you say what is the nature of mass production, it is the manufacturing of large quantities of standardized products, often using assembly line or automation technology. So, when you talk about mass production, we get different elements of mass production. There are three important elements of mass production. If you go through this paragraph, we find there are three important elements of mass production. This is called number one is specialization. Number one is specialization means a worker specializes in producing a particular type of work or product. And standardization. Standardization means it produces identical products. It produces identical products or same products. And there is division of human labor. That means works are divided among the workers or among the labor. That means if a particular work is there, instead of one individual doing all the elements of a work, the work is divided into various elements, and each element is performed at a particular workstation. And in a workstation, different workers are positioned who do that type of work only. So, mass production is based on two general principles, that is, division or specialization of human labor. That is, use of tools, machinery, and other equipments, using automated system in the production process, and there is interchangeable parts and products. Parts can be interchangeable. So the main objective is to ensure that the whole process of manufacturing system remain at the lowest cost possible while turning out at the highest volume possible. Producing product in bulk results in their individual cost being decreased. So when you talk about mass production has an important objective is to see that the whole process of manufacturing remain at the lowest cost. That means the cost of production is the lowest, but on the other hand, it should produce large volumes of product. So producing product in bulk results in individual cost being decreased. So first thing I want to start that again I am saying mass production is manufacturing a large quantity of standardized products, often using assembly line or automatic technology. Yes. So assembly line production, when you talk about mass production, assembly line production goes in hand or it should be taken into consideration. So what is assembly line? Is a production line where materials move continuously at a uniform average rate through a sequence of workstation where assembly work is performed. Typical example of these assembly lines are say car assembly, electrical applications, TV sets, or your computer assemblies, toy manufacturing. All these are example of the arrangement of work along the assembly line will vary according to the size of the product being assembled, the precedence requirement, the available space, the work element, the nature of the work to be performed on the job. So assembly line production is nothing but it is a system where materials move continuously. There is no stoppage of materials movement, raw materials movement. It moves continuously at a uniform average rate. That means in an hour, first hour it moves at a rate of 20, means at the second hour it must be around that. So uniform average rate through a sequence of workstation. Very important. Sequence of workstation. That means their workstations are stationed or positioned in a such a way a sequence is to be maintained. And that means the work which is to be done first, then the workstation performing that work is positioned first. Then the work coming after that will be positioned next. Similarly, the workstation will be positioned. Now, in real world, we find that when you produce car, electrical appliances, TV sets, computer assembly, toy manufacturing, all these are. So, assembly line is a production process that breaks the manufacture of a good into steps that are completed in a predefined sequence. Assembly lines are mostly used method in mass production products. They reduce labor cost and because unskilled work are trained to perform specific tasks. Increasing assembly line manufacturing is characterized by concurrent process, materials, multiple parallel activities that fed into the final assembly stage. So, one of three important characteristics of assembly line is there is a sophisticated communication system, material flow plan, and production schedule. So, to say with assembly line production, with that the work is say divided into assembly line is a production that breaks the manufacture of a good into different parts and that is completed in a predefined sequence. Now, the question arises, where do you go? Where do you go? Yes, before we go to, now we'll discuss what are the, say, advantages we generally get in a assembly line production. First advantage may be speed. Say, automated assembly lines are much faster than manual systems. When you talk about assembly line, it refers to automated technology or automated machinery or automated assemblies. Now, that automated assembly lines are much faster than the manual lines. Accuracy. Automated assembly lines are more accurate than the manual lines. And less labor, since assembly line require less manpower than the manual lines. So, because in assembly line, all the works are performed by machines and say robots. So, the less manpower is required. There is safety. Automated assembly line are safe for use. And talking about the types of assembly line, we have weld assembly, soft weld assembly, then we have revert assembly, sub assembly, partial assembly, full assembly. So there are different types of assembly. So there may be assembly of weld types, soft weld, revert. So assembly line production is to divide the work into different elements and in a predefined sequence. So question arises, where to go for mass production? It's generally agreed that mass production is justified only when production quantities are large and product variety is small. The ideal situation for mass production would be when large volume of one product without any change in design are to be produced continuously for an extended period of time. Now the rate of consumption of the or the demand of the product as compared to the rate of production decides whether continuous or batch production is called for. Obviously, only when the rate of demand is greater than or equal to the production rate, mass or continuous production could be sustained. If the rate of demand is less than the production rate, batch production with suitable inventory, builds up could be resorted. So this thing says that when we go for mass production, first and foremost thing, you must remember that when you prepare large quantity and variety is small. In other words, I can say that when products are standardized, mass production is the most ideal situations. When the products are standardized, we call it ideal situation. Situation for mass would be when large volumes of one product are to be produced continuously within extended period of. The second criteria by which we judge whether we go for mass production or batch production is the demand and the production rate. The rate of consumption or rate of consumptions can also be referred to as demand of a product. If the demand of a product, if I compare, if a production manager or a operation manager compares the demand for the product, the demand of the product with the rate of say production, how much the products are demanded by the consumers and how much I am producing. And if the demand is greater than equal to the production rate, then we have to go on producing continuously. You have to go on. If the demand rate is less, what happens? We can produce in batches and keep in the inventories, and we can inventory build-ups could be resorted. But if the demand is greater or equal to mass production rate, mass production is say justified or mass production is advisable. So first thing is if the product is standardized with little variety or no change in design, we go for mass production. And again, if the demand is greater than or equal to the rate of production, we go for mass productions. Now, there are different types of, say, common flow patterns which you have there in your unit block 1. This I flow is like alphabet I in a straight line. L flow is like a alphabet L. U flow, it is a alphabet U, or it may be S flow, or it may be a circle flow or a O flow. Since the work from one process is fed directly to next small process inventory results. So what he says here, what are the advantages? The advantages is that in a mass production system, the production line may be a different flow, but the point is that suppose there are 4 workstations. The output from the first goes to the as an input to the second. The output of the second goes as an input to the third workstation, and the output of the third goes as an input to the fourth. So there is no say in process inventories. Even if there is there, it may be total production time per unit is short. Why? Because the materials move continuously without any. Since workstations are located so as to minimize the distance between the consecutive operations, material handling is reduced. Since the little skill is usually required by operators at the production line, hence training is simple, short and inexpensive. Simple production planning and control systems are possible. Less space is occupied by work in transit or for temporary. So there are few advantages of say mass production. First, there is less inventory, in-process inventories. Total production time per unit is short, and since the workstations are located so as to minimize the distance between consecutive operations, materials handling is reduced. In this type of mass production, little skill is usually required. Why? Because all our automated machines are there. We have to only know how to operate that machine. So training is simple, short and inexpensive. And simple production planning and control systems are possible. And since the machines are positioned in a straight line or in a U flow, they work transit and less space is required. Now, what are the disadvantages we find in a mass production? Since these stations or work units are positioned in a sequence manner, a breakdown of one machine may lead to complete stoppage of the line that flows the machine. Hence, maintenance repair is a challenging job. This is very important. As you remember, in a mass production system, the machines or the workstations are positioned in a straight line, or that means the machines are arranged in a sequential order. Suppose there are 4 or 5 machines are there. In between them, machine 2 or machine 3 breaks down. That means if machine 2 breaks down, then whatever input the output the machine 1 sends, 2 is not in a position to receive it. Similarly, 1 work is stopped, 2 work is stopped, 3rd work is stopped, 4th machine's work is stopped. So the entire system is jeopardized. The entire system comes to a halt. So maintenance and repair is a challenging task. Since the product decides the layout, changes in product design may require major changes in the layout. This is often expressed by saying assembly lines are inflexible. So mass production or assembly lines are inflexible. Why it is inflexible? There, suppose I have designed to produce a product X. So whatever machines, whatever workstation is required for X, accordingly I have arranged my machine in a sequential order. Suppose I want to have produced, say, anything other than X or Y, some products I want to produce for requirement cost, but my system will not allow me to produce anything other than X. So that's why it's called the inflexible system. The pace of production is determined by the slowest or the bottleneck machine. Line balancing proved to be a major problem with mass manufacturing on assembly line. What is line balancing? I will come to later on. That means if the line balancing is not there, suppose there are 4 machines, all are not working at a uniform rate. Some are working at a faster rate, some are working at a slower rate. So raw in process output is more, but suppose the in process inventory or in process say inventory comes from machine 1 who is faster than machine 2, but machine 2 is not able, is preoccupied with some other earlier work, is not able to receive the materials sent by the machine 1. So there is a bottleneck. So the pace of production is determined by the slowest or the bottleneck machine. So line balancing proves to be a major problem with mass manufacturing on assembly line. So if all the machines or all the operators are of the same, say, efficiency or in the same, say, rate of production, then there may not be any problem. But problem arises when some of the machine workstations are slow in operating. Supervision is general rather than specialized. A supervisor of line is looking after diverse machines on a line. That's one. Here, supervision is general because there are different types of machines. So one individual may not be expert in all types of machine operations. So whatever supervision he gives it of a general nature. Generally, high investments are required going to specialized nature of the machines and there are possible duplications on the line. Yes. So there may be, suppose grinding machines may be duplicated, say grilling machines may be duplicated as per the requirement. So There is high investments also involved here. Generally, high investments are required owing to specialized nature of the machines and possible duplications. Yes. Assembly line balancing is arranging the individual processing and assembly tasks at the workstations so that the total time required at each workstation is approximately the same. Assembly line balancing is strategically planning, locating, and sequencing workstation. Following are the examples where there is a need to balance the assembly line manufacturing. Assembly line, that is manufacturing of automobiles, assembly aircrafts, shipyards production, we require said balancing. Assembly line balancing is nothing but arranging the individual processing and assembly tasks at the workstation so that the time required by each workstation is approximately same. That means we are balancing it. It is useful to consider two types of line balancing problem, assembly line balancing and fabrication line balancing. The distinction refers to the type of operation taking place in the line to be balanced. The term assembly line indicates the production line made of purely assembly operation. The assembly of operations under consideration involve the arrival of individual components parts at the workplaces and the departure of these parts first and together in the form of assembly and sub-assembly. The term fabrication line on the other hand implies a production line made of operations that form the change, the physical or sometimes the chemical characteristics of product involved. Machining or heat treatment would be fall into the operations of this type. So here there is a distinction between assembly line balancing and fabrication line balancing. So before that, I've already told what is balancing. What is balancing? Balancing is arranging the individual tasks, processing and assembly tasks at the workstation so that the total time required for each workstation should be uniform or approximately the same. So assembly line is balancing strategically, planning, locating, and sequencing the workstations. So here in this slide, I want to highlight that what is assembly line balancing, what is fabrication line balancing. Yes. The assembly line indicates the production line made of purely assembly line operations. I have already told you several times what is assembly operations. Assembly operation is nothing. It involves the arrival of individual components at the workplaces, and after its arrival, what it happens? It is put together, fastened together in the form of an assembly or sub-assembly. We join it, and but the term fabrication line on the other hand implies the production line made of operations which change the physical quantity or physical characteristics or chemical characteristics of a product. Yes. Yes. The total job to be done by the assembly line is divided into work elements, and a diagram that describes the ordering in which work elements should be performed is called a precedence diagram. So here there are three jobs. So the first circle may reflect job 1, job 2, job 3. So this is a precedence diagram which shows that job 2 can be performed. The middle one is job 2. The first one is and the last one is job 3. So that means the diagram itself shows, the arrow mark itself shows that after the completion of the job 1, job 2 will taken off, and job 3 will be taken off when job 1 or 2. So this is a precedence diagram. So the total, suppose this particular work is divided into 3 elements, which is reflected by the circles, and the first, second and third, they should be done in a particular precedence or a particular sequence. Yes. What are the best objectives of say assembly line. The broad objective in design is, as you have seen in two important manufacturing development which led to progressive assembly are the concept of interchangeable parts and the concept of division of labor. This permit the progressive assembly of the product as it is transported past relatively fixed assembly station by material handling device such as conveyor. The work elements which have been established through the division of labor principle are assigned to workstation so that all workstation have an nearly an important one. So the broad objective of design is progressive are the concept of interchangeable and this permit progressive assembly. Second is the division of work. The individual work elements are tasks that are grouped into workstation. This station time, which is the sum of the times of the work elements performed at that station, and it should not exceed the cycle time. That means the time taken by a particular workstation is called the station time. And when you fix the station time, it should not exceed your cycle time. The precedence restriction implied by the precedence diagram are not violated. That means in the earlier diagram, I have shown you, in the earlier diagram, I have shown you there are three workstations. The workstation 3 cannot be positioned at first or cannot be positioned in the middle. So this the precedence restriction implied by the precedence diagrams are not violated. That means individual work element tasks then grouped into workstations. So individual work elements or tasks are grouped into workstations. That means this workstation or the task which is to be performed first is positioned in the first position. So the precedent restrictions implied by the precedent diagrams are not violated. There are many possible ways to group these tasks keeping the above restriction in mind. We often use certain criteria like line efficiency, balance delay, smoothness index to measure how good or bad a particular grouping is. So first is your line efficiency. What is line efficiency? This is the total ratio of the total station time to the product of the cycle time and the number of workstations. So this is the ratio of total station time. There are 4 stations, and what are the, if I have 4 workstations, well, 4 workstation time. If you add that, we get the total station time, and to the product we divide it by the to the product cycle time and multiply with the number of workstations. That gives you the line efficiency. Balance delay, BD. This is a measure of the line inefficiency. It is total idle time of all stations as a percentage of total available working time of all stations. So it measures as a percentage. Suppose 10 hours is available and I am idle for 3 hours. So it is the measure of the line efficiency, that is the total idle time of all stations as a percentage of the total. Smoothness index. This is an index to indicate the relative smoothness of a given assembly line. And smoothness index of 0 indicates perfect balance. So if a smoothness index is 0, it indicates a perfect balance. That means the assembly balancing is perfect. So these are the 3 criteria. So assembly line balancing is strategically planning, locating and sequencing workstations. And where you do this, we do this in aircraft manufacturing, do it in say automobile manufacturing, we do it in shipbuilding, etc. So there are different steps in calculating this assembly. Calculate the task time, then perform time studies, identify the bottlenecks and excess capacity, relocate the resources, and make other improvements. So when you do a balancing, assembly line balancing, we generally perform certain steps. That is, we first do the measure the calculate the task time, perform time studies, and identify the bottlenecks. While doing the time study, we can identify what are the bottlenecks and what are the excess capacity, and relocate the resources and make other improvements. Now, two important gentlemen have developed a model called Kilbridge and Webster method. In this procedure proposed by Kilbridge and Webster numbers, then numbers according to this, numbers are assigned to each operation, deciding how many predecessor it has. Operations with the lowest predecessor numbers are assigned the first to the workstation. The procedure consists of the following steps. Now, here in this method, I have told you 1, 2, 3. That 3 has the maximum predecessor, 2 and 1. And 1 has no predecessor at all. So, in this model, what you do, numbers are assigned 1, 2, 3, 4, 5, 6. Actually, we find which of the element has the lowest predecessor, and we construct the precedence diagram for the work elements. In the precedence diagram, list in column 1 all work, make a column 1, list in column 1 all work elements that not follow others. That means you have to see what are the work element that need not follow others. And in column 2, list work element that must follow in column 1, continue to the other column in the same way. By constructing the column, the elements within a column can be assigned to workstation in any order, provided all the elements of the previous columns have been assigned. Then select a feasible cycle time. Then assign work elements to the station such that the sum of the elements times does not exceed the cycle time. This assignment proceeds from column 1 to column 2 and so on, breaking intra-column ties using the criteria minimum number of predecessors. Delete the assigned elements from the total number of work elements and repeat step 3. If the station time exceeds the cycle time CT due to the inclusion of certain work element, this work element should be assigned to the next station. Repeat steps 3 and 5 until all elements are assigned to the workstations. Then Helpson and Briney method. This is also a method of, say, assembly line. So determine the positional weight of each work element. That means we have to find out the importance of each work element. Rank the work element based on the positional element in this step. The work element with the highest positional weight, proceed to the assign the work element to the workstation where the elements of the highest positional weight and ranked are assigned first. If any workstation additional time remains after assignment of an operation, assign the next succeeding ranked operation to the workstation, as long as the operation does not violate the precedence relationship and the session time does not exceed the cycle time. This is important. Repeat step 4. If you go through your study materials, you can find how the problems are done. But this is the different methods, this is the steps. First, we have to find out the positional weight of each workstation. Then rank the work elements on the positional weight. Then we have to assign the work element to the workstation which has the highest positional weight. If any time is left out, then next highest ranked operation, as long as the operation does not violate the precedence rule and the station time also does not exceed the cycle time. Equal amount of work to do. Each worker at his station is assigned certain of the work element. The worker performs them repeatedly on each production until it passes. The assembly line balancing is generally one of minimizing the total amount of idle time or equivalently minimizing the number of operators to do a given amount of work at a given assembly line speed. Balance delay is defined as the amount of idle time for the entire assembly line as a fraction of total. This I have already discussed. Yes. So, assembly line balancing problem is generally one of minimizing the total amount of idle time or equivalently minimizing the total number of operators to do a given amount of work at a given assembly line speed. This is also known as minimizing balance delay. Balance delay is defined as the amount of idle time for the entire assembly line as a fraction of the total working time resulting from the unequal task time assigned to various stations. Gilbridge and Wester, after studying the variation in idle time at stations caused by different assembly line balances, conducted that high balance delay for an assembly line systems for a specific product is caused by wide range of work elements, large amount of inflexible line mechanization, indiscrimination choice of cycle times. However, as we will see, the cycle time is often dictated by a specific desired production rate, which may not lead to low balance delay. So, Gilbridge and Wester has made an extensive study and at stations caused by different, what are the variations, why there is high balance delay is because of the various important wide range of work elements, large amount of inflexible line mechanism, and indiscriminated choice of the cycle time. Now, what are the problems and prospects of this? In both line balancing methods discussed in the previous, it was assumed that work element times are constant. In practice, these times may be varying randomly owing to factors like human variability, fatigue, carelessness on the operator's part. Even in case of machine operation, the setup or positioning time of the part or components could lead to a random variation in individual work element times. Since assembly line is balanced for a given set of work element times, the effect of these variabilities are twofold: greater idle time at some workstation and reduction of average production rate of the line. So, in theory or in model, we have assumed that the time of the work element are constant. But in practice, it may not be possible at all because the work elements are performed by the human beings, and human beings are not robots or they are not machines. So some variabilities are there, some fatigueness creeps into, and some carelessness on the part of the operators. Even if in machine operation, there is some setup time, there is some breakdown, positioning time could be lead to random variation. So we cannot always assume that the time taken by all the say workstations will be same. There must be some variability. Yes, problems, breakdowns at workstation. And mass production system consists of number of stages in a series at which some operations are performed. A failure or a breakdown in one stage or workstation will result in the failure of the entire production system until repair is completed. The result could be decreased production rate. The problem is handled in practice by providing efficient maintenance service so that breakdown units are repaired and put into service as soon as possible. Buffer storage of semi-finished goods between each pair of stages so that entire line does not stop due to failure of one of the more units. So, second important problem is breakdown at workstation. If the breakdown occurs in any one of the workstation, the entire system will break down. The entire system will fail, and it will and unless it is repaired, the workstations will not come into will not deliver. So if the breakdown occurs, it will result decreased production rate, and these problems can be overcome by two efficient maintenance service so that whenever a breakdowns occur, it should be taken into consideration, it should be repaired immediately. Or you can maintain a buffer stock of the semi-finished products or in-process products between stage of pair of stages. Suppose there are three machines, 1 to 2, 2 to 3, or 2 to 4. We should keep some inventories of the semi-finished products of machine A, or we can keep some of the, even if the machine 2 say or goes wrong, we can get this product of the semi-finished product of the machine 2, which we can feed to machine 3. The question of how much buffer storage to allocate between stages is of great practical importance. If you keep higher buffer stock means greater tide of capital and lower risk of runout and subsequent line stoppage due to breakdowns. The decision to estimate the size of the buffer stocks can be governed by one or more of the following criteria, which consider as to what is the buffer size. That is, maximize the production rate of the system, minimizes the total production cost, and maximizes the availability of the production system. So, in the last slide, we have told you one of the remedy for this failure is to maintain buffer stock. But the question arises, how much buffer stock we should maintain? If you maintain too much of buffer stock, then our capital is tied up. But too much buffer stocks will also one advantage that will have lower risk of runout and subsequent stoppage. So when you take a decision, what is our buffer stock size? We take into three important criteria. That is, it should be maximize our production rate, it should minimize our production cost, it should also maximize the availability of the production system. Then multi-product line. One of the major disadvantages with product line is the relative inflexibility. A line is usually designed for one product, and changes in the design of the product can often difficult to accommodate on the line unless suitable adjustments are made at the workstation. But when similar products in which a large percent of the tasks are common have to be manufactured, the possibility of the same production line of the products can be explored. Since tasks are fixed with station, once balanced, it should be apparent that station times and efficiency will vary with products being produced. A great variety is in this difficulty might dictate that separate lines are utilized. In case a multi-product line is to be designed, a common precedent diagram must be developed. So, one of the major disadvantages what I am talking about assembly line is relative inflexibility. That means the assembly line is meant to produce a particular type of product. If there is any changes, then we cannot accommodate that change unless we change our workstation. But when a similar product in which a large percentage of tasks are common have to be manufactured, then the possibility of same production line for the products can be explored. So if a large percent of the tasks are common, suppose there are similar products which require a, say 80% of the work of the products are similar, then we can consider a multi-product line. So yes, what is modular production? In modular production, we tend to specialize in the production of particular parts or activity that that can then included as components of more than one product or service. The reason for wanting to achieve such a commodity is that one part or operation, if used in several product and service, can accumulate sufficient demand volume to warrant a investment in a flow sum. Yes, that's what he's saying. If a components can be used more than one product or service, suppose a picture tube can be used in a computer and can be used in a TV or a monitor or a LCD screen, which can be used in both the products, in both components. So the reason for modular production is, what is the advantage of modular production is that if a particular commodity, if to achieve such a commodity is one part or operation, if used in several products and service, the demand for that sufficient demand for that part or operation will increase, so that we can invest in a flow shop or a mass production shop. Yes. Group technology provides another aspect of the same basic idea. It refers to specialization in families of similar parts, hence components requiring primarily turning operations such as shafts are collected in one group, while components requiring surface grinding, drilling operation such as plates are arranged to a different group. These groups become the basis on which a traditional process plant layout can be recognized in a group technology. Plant layout in which machines are arranged in such a way that each machine is assigned to the production of one group of parts. Group technology typically affects only the component manufacture, not the assembly stage of production. Yes. What is saying in group technology? In group technology, or sometimes called as cellular type of layout, we create different cells, we create different types of department, and each department we keep some similar type of machines. As an example, each cell or each group specializes in producing a similar types of parts. Similar types of parts. Suppose while components requiring, suppose I want to produce component A, that component requires surface grinding and drilling operation, such as plates are grouped into a group. Suppose I want to produce a part B which require turning operations, such as shafts. I want to produce shafts, I require turning operations. So I require keep turning operations into one. So group technology is nothing. It is arrangement of, say, or refer to specialization in families of similar parts. Only one group technology typically affects only the components manufacture, not the assembly stage products. Then automation and robotics. Yes. Mass production has been assigned to large extent by automation and robotics in recent past. Automation refers to generally to bringing together three basic building blocks: machine tools, material handling, and control. Often, considerable amount of time is spent to load machine and unload work and to convey it between to the single operation machines. This restriction has partly been relieved by development of multiple spindle machines. With this machine, a single motor driving several spindles through a great train allow the multiple operations to be performed by one machine. Machine time cycles does not change, but more machining operations can be performed with each cycle. And several machining operations can be performed on one machine by single operators. Then industrial robotics. An industrial robot is defined by Robot Institute of America, which is a programmable, multifunction manipulator designed to move material, parts, tools, or specialized devices through variable program motions for the performance of various tasks. What separates an industrial robot from other types of automation is that it can be reprogrammed for different applications, and robots falls into the headline of flexible automations as opposed to hard or dedicated automation. So, in single words, I can say robots, industrial robots are flexible automations. They are programmed for a particular work. A program is written. Multi-functions manipulator designed to move. A robot is designed to move materials, parts, tools, or specialized devices through variable program motions. And what is different between the ordinary automations and robotic? Ordinary automations are dedicated, or say we can say rigid automations. There is no flexibility. But whereas industrial robots are flexible automation, where any change is required, then it can be reprogrammed. The industrial robot consists of three basic components: the manipulator, the arm, which is a series of mechanical linkages and joints capable of movement in various directions to perform the work task. Number two is the controller, which actually directs the movements and operations performed by the manipulator. The controller may be an integral part of the manipulator or may be housed in a separate cabinet. The power source, which provides energy to the actuators on the arm. The power source may be different types. It may be electrical, hydraulic, or pneumatic. The major reasons for the use of robots in industries are increased productivity. Why use industrial robotics? Because it leads to increased productivity. You can easily adopt it. It is also safe in use, easy of training, return on investment. Our ROI is very high, and greater reliability. That means they do things rightly. Robots are currently in operations in welding and assembly line, drilling and routing, inspection, material handling, machine loading, die casting, and variety other applications. So, industrial robots has three parts. One is the manipulator, second is the controller. Manipulator has a series of mechanical linkages, joints, which are capable of making the movements of various directions. There is a controller part which generally directs the movements in which direction the part should move is given direction from the controller. And there is a power which provides the energy, and this may be different types. So robots are widely used in today's world. They are in use in welding and assembly and drilling, routing and inspection. All types of works are now increasingly done by robots.